Okay, so in our last video we looked at nucleophilic substitution and we looked at SN2 reaction mechanisms. In this video we'll look at SN1. So for SN1, same thing, everything means the same thing, only now we're looking at a first order reaction. So still this means nucleophilic, and this also means substitution over here. Oops. Okay, but yeah, the main difference is these are first order. And let's take a look at what this looks like in a generic sense. The mechanism is just different. So I've got my leaving group on it. And so in SN2, the nucleophile comes in and it kind of helps the leaving group leave. You know, it starts forming a bond to this antibonding orbital and sort of sets things off. In an SN1 reaction, the leaving group has to pop off first. And then in a second step, the nucleophile can come in and react to form, I'll just put a mega charge in there, to form whatever the product's going to be. So you can see in this example that the order of the reaction doesn't really have anything to do with the number, I mean, maybe loosely it does, but it's not directly related to the number of steps involved in the mechanism. Here we have this first step, and we also have a second step here, but the reaction is first order. The order of a reaction refers not to the number of steps at all. It's related to, as we said in the last video, the number of molecules that are involved in the rate determining step of the reaction. And so when we look at this reaction, the rate determining step is just going to get rid of that altogether. The rate determining step is this. As you might imagine, it takes a long time, or it's a very slow, I don't know if you imagine this or not, but it's not a very, carbocations don't form very easily. And so if that's the first step in the reaction, it has to take place spontaneously. That's kind of the holdup for everything taking place. And so the reaction itself is only dependent on the concentration of the substrate. So in this case, that would be okay. So I got my leaving group there. So the concentration of the nucleophile doesn't matter because this takes forever to form, and then as soon as it forms, the nucleophile can come in and attack and then form the product. But the rate is determined by the slowest step in the overall scheme. And this is true of anything that's done in serial, right? If you look at a manufacturing plant and you want to speed up a process, you don't look at the really fast parts and think about speeding those up, right? If I'm working on an assembly line, I'm not trying to speed up the fast parts, or speeding up the fast parts of the assembly line doesn't make anything faster. I have to go to the slowest part, the bottleneck, and figure out a way to speed that up, right? So anything that's built in serial, or done in serial, like a sequence of things, is rate limited by whatever the slowest step is. And so in chemistry, we call that the rate determining step, but it's just generally true of anything that happens kind of linearly. And you can think about that in the context of anything you want, right? You can think about it in terms of baking, you can think about it in terms of building a house. The slowest step, though, is what you have to speed up if you want to speed up the overall process. Okay. So yeah, so we've got this general reaction scheme. Let's look at an actual reaction. So generally, these are done actually, let's look at this one. So I'm going to use another nucleophile. Let's say I have chloride in there. If you're just looking at the overall reaction, it can be hard to say whether or not this took place via SN1 or SN2, because I had my leaving group, I had my nucleophile, it substituted out. The leaving group did leave, just like it would in an SN2 reaction. So, in the absence of understanding the mechanism, the overall reaction is very similar. But we can actually predict which one happened just by analysis of the substrate and the nucleophile. And that's what we're going to spend some time learning. But some things to look at here, and we haven't really talked that much about the nucleophile and its role. We're going to get to that though. So remember that in the, when we looked at SN2, we thought, what's going to speed up, what's going to be the fastest for an SN2? If we're looking at methyl iodide versus a primary versus a tertiary. Oh my goodness, here, let me start over. Let's say I'm looking at methyl iodide, and then I'm comparing it to a primary versus a secondary versus a tertiary. What am I going to expect for the rate here? Well, if the rate determining step depends on the formation of the carbocation, which of these do we think is going to form fastest? And this is something we can answer based on what we already know, which is the series for carbocation stability. If we're looking at these different carbocations, which of these do we expect to be the most stable, which we can say, which is more or less saying the same thing of like which of these is going to be formed the fastest. You could try if you want to, if you remember from the radical chapter, relate that back to Hammond's postulate. Which of these are we going to expect to form the fastest? We're going to expect this one to form the fastest, right? That's going to be the most stable one. So how does the rate of SN1 change? It's going to increase in this reaction. So the more substituted a carbon is, the more likely it is to undergo SN1 reactivity. Okay? So you can see that the SN1 and SN2 reactivities sort of work opposite to one another. SN2 is fastest with the least substitution. SN1 is fastest, or most competitive, I guess you'd say, when it's, I guess fastest works. It's the fastest when it's the most substituted carbon. Right, so SN2, least substituted, is favored by less substituted carbons that are attached to the leaving group. SN1 is favored by more substitution around the carbonary atom. All right, so in SN2, so this is another way that you'd be able to kind of differentiate between these. In SN2, we could look at the stereochemistry, and we knew that if it was SN2, we know if it's SN2, we expect the stereochemistry to get completely inverted. In an SN1 reaction, what do we expect to happen? Well, we kind of know this already because we've looked at carbocations before. If in the first step the iodide has to pop off, what are we going to form here? We're going to form this planar carbocation here. And then so what is going to be, what's our product going to be? Well, the probability of the chloride attacking from the top is the same as the probability of attacking from the bottom. And so what we're going to end up seeing is just a 50-50 split here. Okay? So if it attacks from the top, chloride attacks from the top, let's say, put some color on that. It's coming in this direction. What we're going to see is, as the chloride bond forms, it's going to push down, and this is what's happening in the other reactions. I don't know if we went through it in this much detail, but it's going to push these groups down, and that's going to give you one of your stereoisomers. Okay, and you can check that for yourself if you want to assign R and S to that. If it comes from the other side, so different reaction, Obviously, it can't approach both at the same time. But yeah, so if it does this first one, this is what we end up with. If it goes through the second one, though, we're going to see that it pushes them in the opposite direction. And that's going to give us whatever the opposite stereoisomer is. And since the probability of it happening is 50-50, you're just going to end up with a racemic mixture. Yeah, so I'm trying to assign this in my head really quick. So I think this would be the S stereoisomer, and this would be the R stereoisomer. Yeah. So you can see that approach from the top or the bottom leads to each enantiomer, and this explains why when you start with something, and when you have an achiral molecule, you always end up forming something racemic. So it doesn't really matter here. So if you started with 100% R here, let's say, of whatever this is, what you end up with, no matter what, is a racemic mixture. And the reason for that is that the intermediate here is achiral. So whatever information was stored, if you want to think of, if you want to think about it in terms of information, here I have this information about this molecule that it was 100% R. And that information is held in the three-dimensional orientation of all these different substituents to each other. But as soon as I lose my leaving group, carried away with my pen again. As soon as I lose my leaving group, as soon as I lose this, and I go to this intermediate here, that information is lost, right? I don't know if that molecule started out as R or S because it's not chiral anymore. So it's erased its sort of chiral, the chiral information from that molecule. And once that chirality is erased, the only outcome that you can really have is that you're going to end up with a 50-50 mix of R and S, at least in our class, right? Unless you're using something really fancy, some kind of fancy reagent. So the expectation is for this to be racemic, and that's what we end up seeing, regardless of what you start with. You could start with a racemic mixture, you could start with 100% S, you could start with a 70% S, 30% R. It doesn't really matter. In the end, you're just going to end up with a racemic mixture because the intermediate you go through is achiral. So if stereochemistry is not your jam, you know, what do you have to remember here for stereochemistry? Not anything really new. It's just that if I start with something, well, I guess it's just that always are almost always racemic. So there are times where you don't see just a purely racemic mixture, and that's where your mechanism is caught somewhere in between an SN2 and an SN1, and your leaving group didn't fully leave, and it's blocking one side and all this kind of stuff. Yeah, okay, sure. Things are always more complicated if you look more deeply at them. We're not going to get into detail on that. So for my class, at least, if it goes SN1, you end up with a racemic mixture, no matter what the stereochemistry of the starting material is. Okay? Okay, so that's SN1, and then we also know SN2 from our last video. And then we're going to take a break from we're going to look at two more mechanisms ultimately. We're going to kind of take a break from looking at just straight up mechanisms, and we're going to go a little bit deeper into looking at leaving groups and nucleophiles and things of that nature. And then we're going to tie that back into SN2 and SN1 and see how we can put everything together to predict whether something's going to go through SN2 or SN1, okay? So it's a little bit of a path here getting through this chapter, but stay with me, and it's all going to kind of come together you know, as nicely as this stuff can come together. It's kind of wonky, but this is just kind of part of the canon of stuff that we teach. And you know, I guess it sounds like I'm dismissive of it as being really useful. It's actually really useful. These are really good ways to think about chemistry, and I encourage you guys to really dig deep on this, because if you can hold this chapter and understand not just how to predict what's going to happen, which I think where a lot of students end up, but actually understand why things happen, then you have like this really great predictive power that you can apply anywhere in your organic chemistry course, and the second one as well. And that's a lot more powerful than just being able to kind of memorize a roadmap or a set of heuristics and answer the right question. So do your best to try to understand this stuff at a fundamental level, I guess is what I'm saying.